Okay, hello everyone. We have trig functions and graphs, lesson 8. We're continuing with transformations of trig functions. In lesson 7 we looked at vertical and horizontal stretches, or in other words, the effect on amplitude of a trig function, and the horizontal stretch, the effect on period of a function. So we are going to be looking at today now the translations, the left-right and the up-down. So we're going to be looking at the entire picture, all of it together. We've got our vertical stretch, horizontal phase shift, we'll get into that, but the horizontal translation and then the vertical translation for both sine and cosine. They're really the same idea there. Okay, so let's take a look at example number 1. Describe how the graph of a given function compares to the graph of y equals sine x, where x is in degrees. Okay, so just think back to transformations here. If I've replaced x right here with x minus 30 degrees, that would be a horizontal translation right 30 degrees. Okay, and now let's look at the next one, sine x plus 2. Okay, this one can be tricky for some students because some students see it like that and think that it's left 2. Well, it is not. Okay, don't do that. You assume, if there's no brackets around it, you assume that only the x is inside the sine function. So the plus 2 is outside of the sine function. And as you recall, that would be a vertical translation of up 2. Okay, next one. Actually, you try the next two and we'll check and see if we have the same answer, okay? So pause your video and go ahead and do the next two. Okay, so did you guys get left 60 and down 1 for this one? X plus 60 and minus 1. Okay, and the next one, we can do this one with the 45 on the left side with y, in which case it would be opposite. You would think down, but it's actually up 45, or you can move that to the right-hand side. And inside the brackets here, that's affecting x, so it's moving right 45 degrees. All right, so they like to call things different things. Or what I mean is, horizontal translation now, when we're talking about trig, is called horizontal phase shift. Mostly it's got to do with the actual practical application of trig functions, and phase shift in particular applies to one real-life application I know of is electrical current. So that is probably why they're renaming that. Okay, and vertical translation is now called vertical displacement, and again it's related to the real-life application of trig functions. All right, so let's see what we can do to fill in this table here. Complete the table to describe how the graph of the given function compares to the graph of y equals sine x, where x is in radians. Use a graphing calculator if necessary. I don't think we'll need that. Okay, so horizontal phase shift. Okay, first of all, I guess you could use your graphing calculator for this, but the sine function, if you recall from lesson 6, looks like that. Now the key thing there is this point right here. The halfway point from bottom to top, so halfway, is on the y-axis. Okay, that's what you have to remember. That point, if it's been moved left or right, that means there's been a horizontal phase shift. That's if we have the graph and we're trying to get the phase shift. In this case, so originally horizontal phase shift would be 0 or none, if you like. And vertical displacement would again be 0 or none. Okay, now let's look at the equation. We have replaced x with x minus pi over 4, so think transformations. That should be pi over 4 to the right. Okay, is there any vertical displacement? No, there's nothing being added at the end or over with the y, so again 0 or none, either one. All right, next one, sine x plus 5. Don't get sucked in on this one. Remember what we talked about in the previous example. That plus 5 is not inside with the x. So that would mean there would be no horizontal phase shift, so none. And vertical would actually be the 5, so it would be up 5. Good. Okay, why don't you guys try the next one, and then you could try this one with the variables as well. Just because it's variables doesn't mean there's anything weird or different. So give that a try as well. So pause your video, try those two. Okay, so for the next one, we should have gotten that it moved left pi over 2, 3 pi over 2, and this plus pi over here with y, you could subtract it to the other side, but when it's with the y, it's opposite, so it would be down pi rather than up pi. And then the last two are just the generic version of that. So if you have x minus c, that would move us right c. If we have plus d at the end, that would move up d. And the next one's exactly the same. And then they say, would you expect similar effects on the graph of y equals cos? Yes, we would, because the cos function, it really, other than being moved over a little bit, behaves exactly the same way as the sine function, except for the starting point, which is the peak is on the y-axis. All right, let's take a look at the next page. Okay, so they summarize what we just discovered there about the phase shift and the vertical displacement. And if you have the graph and you're trying to find the d value or the vertical displacement, this formula can be very handy. You take the max plus the min divided by 2. That's because the vertical displacement really is the average of the y values. Okay, so then they just kind of summarize it all here. And again, as I said before, tan, we do not need to worry about the different transformations of tan in Math 30-1. All right, so we summarized how to find amplitude. It's the absolute value of A if we have the equation. If we have the graph, it's max minus the min divided by 2. Period, if we're in degrees, we go 360 divided by b. That's when we have the equation. Or 2 pi divided by b if it's in radians. How do we tell if it's in radians? Or degrees? Degrees, there'll be a little degree symbol on that bracket right there. For radians, they just won't say anything at all, so you assume it's in radians. Okay, horizontal phase shift, left, right, vertical displacement, up or down, and from the graph, max plus the min divided by 2. All right, let's look at the next page. Okay, consider equations of the form y equals a yada yada, the full transformed form, and cosine as well, where a is 1 and b is 1. So they're implying we don't have any horizontal or vertical stretches going on. Okay, so write the equation which represents a cosine function. So we know we're writing y equals cos. Okay, having a horizontal phase shift of 75 degrees right. Okay, so check out our variable, it's x. Okay, and since we are moving left or right, you need brackets here so that it's all inside the cosine function, meaning x was replaced with x, what would that be? X minus 75 degrees, right? So we'll go like that, minus 75 degrees, and there we go. That's our equation. Why don't you guys try B, and we'll see if we get the same answer for the equation. So pause your video, please. Okay, so did you guys get this equation as well? Y equals sine bracket x plus 3 pi over 5, because it was left, so that's why the plus sign, and the bracket, and then it moved up 4, so plus 4 at the very end. All right, good job. Next, find the amplitude, period, horizontal phase shift, and vertical displacement of the graphs of the following functions defined on x is now in the reals, so that just means it goes forever. Okay, so we're given the equation. We have to answer those questions. So first of all, amplitude. Okay, so amplitude is the absolute value of the number in front of the trig function. So in this case, absolute value of 2, which would just be 2. All right, period. Period is 2 pi if we're in radians. Are we in radians? Let's take a look. Ah, yes, we have a pi inside with x, so we're in radians. 2 pi divided by our b value. Well, our b value is the number in front of x. And really, that's our horizontal stretch, so that's what should affect our period. Okay, so 2 pi divided by our b of 3, and there we go. No reducing to do, so that should be our equation. All right, horizontal phase shift. I'm going to abbreviate that, HPS. Okay, so when you describe the horizontal phase shift, you actually have to give a direction, left or right. So if we look inside here, x would have been replaced with x plus pi. So because it's plus, it was moved left pi units. Okay, now vertical displacement, I'll just refer to that as VD. Okay, you check out this part, the minus 4, so that tells us our graph was moved down 4. And there we go. Okay, I always do the easy one and then tell you guys to do the hard one. How nice of me. Okay, so you guys are going to try B and take a stab at that, and then we'll check back and see if we have the same answer. Okay, pause your video, please. Okay, so check your answers, see if we got the same thing. Amplitude, remember it's the absolute value of the A in front. The negative is just a reflection, it does not affect amplitude. Period, so that's affected by our vertical stretch, which is related to B. Sorry, horizontal stretch, which is related to B. So period would equal 2 pi over our B value, which is 1/4. Now we have basically a fraction within a fraction, so think of it this way. 2 pi divided by 1/4 would be the same as multiplying by the reciprocal. So 2 pi times 4 over 1 equals 8 pi. Now let's say you're not a fan of fractions. What you could do is do this part on your calculator, but make sure you have brackets around that fraction, and then throw pi back in at the end. Okay. Horizontal phase shift, since it's minus, it's being moved right, pi over 12, and then up 3. Okay, good. Let's look at the next example. Okay, again, find amplitude, period, all that stuff. Now, take a look at this equation. Doesn't that look a little familiar? Doesn't that look an awful lot like this one up here? But compare it. What's different? Well, the thing I'm noticing is this 3 is in front of a bracket here, whereas here it's immediately in front of x. Think back. You did some of these in the transformations unit. When you have this number, the horizontal stretch, immediately in front of the x, then this part is not the true horizontal translation. So you need to, first of all, before we do anything, factor that 3 out of both terms. So when you factor it out, you're dividing it out, which means you'll have pi over 3 and then minus 4. And there we go. Good. Now we can actually see what our horizontal phase shift would be. Before we would have thought left pi, but we'd be wrong. Okay, so run through that again. Amplitude equals 2, and you could probably fill that in. Okay, and then make sure you do this next one as well, and take note that 2 is immediately in front of the x, so you need to fix that first before you fill in what the horizontal phase shift is. Okay, so you guys work on those 2 examples, and then we'll check back and see if you got the same as what I did. Okay, so pause your video and complete those 2. Thank you. Okay, so on the first part here, we should have had an amplitude of 2, period of 2 pi over the b, which is 3, and horizontal phase shift pi over 3 left, and vertical displacement down 4 from the negative 4. Okay, now this one a little bit trickier. Hopefully you remembered, hey, I got to factor that 2 out. So we factored the 2 out, but then we have a fraction divided by 2. Okay, so off to the side, here's what I suggest you do. Take what you're factoring out. Factoring out means dividing, so you literally take pi over 2 divided by 2. Now dividing, when you have fractions going on, I would change that to multiplying by the reciprocal of 2. So pi over 2 times 1 over 2. Then you multiply across on the numerator, pi times 1, which is pi, multiply the denominators, 2 times 2, which is 4. And now we have our true horizontal phase shift. Okay, amplitude is the absolute value of the number in front of cos. In this case, it's a negative 1, so the absolute value, positive 1, period, 2 pi over 2, the b value, which is pi. The b value is 2, 2 pi over 2 equals pi. Horizontal phase shift would have been pi over 4 to the right, and vertical displacement up pi. All right, good job. Compare your answer to. So pretty much what should be different for those is the phase shift. Okay, let's look at the next page. Okay, in example 6, they're saying the graphs from A to D represent the same trig function. Okay, and if you'll notice, the graphs, yes they are, they're exactly the same. Okay, exactly the same position. But what they're going to have us do on this example is write that the equation for that graph in 4 different ways, so a different equation for each one. Okay, so first of all, we have write the equation of the graph in the form y equals a sine x minus c, where a is greater than 0. So they're saying a is not negative, so it hasn't been reflected. And there is a minimum possible horizontal phase shift. Okay, so minimum possible horizontal phase shift. All right, now we're talking about a sine graph. When you're doing phase shift, you have to think about what a sine graph normally is. And a sine graph normally has that midpoint halfway between bottom and top is on the y-axis. So we're going to look for that point. Now we are running out of time, so I'm going to continue this in part 2 of lesson 8. See you there.